gente, bem-vindos a mais um colóquio do IME. Esse é o último do semestre, a gente espera que semestre que vem tenha pelo menos outros 4 ou 5, a gente tem tentado fazer um por mês, e a gente tem também feito um esforço bastante grande de fazer com que as palestras sejam interessantes e acessíveis, né, para um público bastante diverso e tal. Então, espero que vocês estejam gostando e podem fazer propaganda do colóquio aí também para ver se mais gente vem. Então, eu vou agora deixar com o Sinai, que vai apresentar o Rafael, que vai dar a palestra de hoje.
Eu vou apresentar rapidamente. Então, é muito prazer ter conosco Rafael Benguria, português ou inglês? Tanto faz.
Yeah.
So I guess I can speak English because Rafael will give the lecture in English. So.
No, but you can speak Brazilian Portuguese. I'm speaking English.
So
but I understand.
No, but anyway, it's really very, very excited to have Rafael here, an extremely noted scientist, a physicist by trade, but to me he's a mathematician, but to many other people he's a physicist, and he's really, I would say, both. So he had many honors. Born in Chile, he got his PhD in Princeton in 1979 with Lieb, Professor Lieb in Princeton, and National Prize for Exact Sciences, 2005, Chilean Academy of Sciences, and so on and so on. But we should let Rafael speak. Thank you very much for coming.
Thank you very much, Sinai. I would like to thank all the people that invited me, but in particular Sinai, Marcone, and Andres. And it's a pleasure for me to be here. I apologize for not speaking Portuguese. I've done talks in Portuguese, but it's a disaster, so I prefer not to. And I've been many times in Brazil, and in particular in USP, I've been like 4 or 5 times. I think this is my 5th time. And it's always great to come back here, and I see the progress. I mean, the first time I was here was in 2002. So 22 years ago, and it's very nice to see how it evolves and all that. I mean, for me, it's a pleasure to be at this very important university. Anyway, so thank you very much. I apologize for the technical problems to begin with. And so my colloquium here is going to be rather general. I'm going to talk about the isoperimetric inequalities in general, and I'm going to start with the more classical one. And the very first isoperimetric inequality that appears in the history was the classical isoperimetric inequality that appears already in the Aeneid of Virgilio, and when he comments on the foundation of Carthago. And then you've probably seen that part, but anyway, the problem is to find the shape of a curve for which, of fixed length, for which you enclose the largest area. That's a classical isoperimetric inequality. And of course, everybody guesses that the right answer there. The right answer is that if you want to enclose the largest area with a fixed perimeter, so draw a circle. And in the foundation of Carthago, it was a semicircle, because I mean you also had one of the sides was the coast, and so that's a origin. I mean, and then this problem has appeared many times, and it wasn't solved completely until Weierstrass came with the perfect solution at the end of the 19th century. But there are many aspects of this problem that were already known for the ancient Greeks. And one of the simplest version of the isoperimetric inequality was solved by Euclid himself, and he considered the same problem but restricted to the family of rectangles. So suppose you have a family of rectangles, all of them of the same perimeter. So you have 2 sides, A and B, and the perimeter is twice A plus B. And of all the rectangles of the same perimeter, the one that maximizes the area is the square. And there's a connection with a little connection with analysis there. The connection is that which is written at the bottom there, So in terms of the in terms of averages, it says that the geometric average, the square root of AB, is always less or equal than the arithmetic average. So that's the connection, the analytical connection of the isoperimetric inequality for rectangles. And that was proven already by Euclid in the Elements. And there is a huge literature on this problem. And I didn't want to write the whole literature, but one of the nicest articles on the isoperimetric problem was written by Osserman in connection with the International Congress of Mathematicians, and that's a beautiful article written in the Bulletin of the American Mathematical Society in '78. And also there are many works by Giorgio Talenti, who is one of the key figures in this area, and he wrote this a very nice article in the Handbook of Convex Geometry in 1993. But then these are two examples. There are a huge number of examples. And one of the craziest things I ever did in my life was we organized a meeting. I learned this problem of the foundation of Cartago, the problem of Quindido. I learned it when I was a student in physics in classical mechanics. I mean, when I was studying Lagrangians and Hamiltonians and all that. And one of the first examples of optimization that they gave us was the Quindido's problem. So I had this sort of like crazy idea in my head that one day I will be able to visit the site where the whole thing happened, the foundation of Cartago. And unfortunately that happened. I mean, it's a crazy idea. I wouldn't do it again, but we organized a conference in May of 2010 there. And that's a picture, that's a famous picture from the Renaissance, where they are describing the foundation of Cartago, and she's Quindido, and she's ordering someone to cut the skin of an ox, I think, and then she was making a robe with the skin, and then to have the largest possible length of the robe, and then she would surround a piece of land that she was going to be given by the local people in North Africa when she came. But anyway, that's a description of the night. And there are, when you have, so I'm not going to talk about that problem only, but when you have a domain, say in R2, the domain omega, and there are lots of different, and this domain has a fixed perimeter, there are many different quantities that you can associate, I mean, many different quantities with the unit of length that you can associate to this domain. And one of them is the length, I mean, of the perimeter, L, or the square root of A is also a length. And you can also have a diameter, which is the longest distance between 2 points inside the domain. You can have something called the in radius, which is the radius of the largest circle that can be inscribed inside the domain. I try to make I mean, I don't know how to draw with the computer software, but I did that by handwriting. I tried to do my best, but probably I don't know whether they're okay. And in particular, the domain looks like a little, like a piece of, like a tooth. And then, yeah, but it took me a long time. And this is the outer radius, the radius of the smallest circle that can inscribe your domain. So there are lots of different quantities that come from geometry, and all of them, they have the dimension of a length, and you can compare them, and you can ask yourself, and the same thing as in the classical isoperimetric inequality. It has the dimension of length square, and you can compare it with L square, and then you try to optimize the quotient. But you can do the same thing for all the other quantities that are described there. But one of the things that you can do is also use mechanics. And the simple problem in mechanics, I mean, is you consider the wave equation here in this problem. So you can put a membrane here in the domain, and you can tap it, and then it's going to vibrate. And the frequencies of the vibrations are related to the solution of this So this is called the Helmholtz equation. So you have the eigenvalue problem minus Laplacian u is equal to lambda u in omega, and with the, say, there are different boundary conditions, but what I chose here is the Dirichlet boundary condition, so the boundary is fixed. So you have a membrane enclosed in this domain, and you tap it a little bit, and then there are going to be the different frequencies. I mean, the frequency, lambda is related to the square of the frequencies. So the square root of lambdas are the frequencies, the natural frequencies of this domain. And of course, if you see this equation and you compare the right side and the left side, the left side here has a unit of 1 over length squared. This is the Laplacian. So lambda has a length, a dimension of 1 over length squared. And so since lambda has a geometrical meaning, so it has the dimension of 1 over length squared, you can compare it also with the other quantities I was describing there. And excuse me?
I'm saying, is the set of all lambdas for human region?
Yeah, I'm going to describe that later on more. So I'm just quoting this problem, but I'm going to say precisely what I meant by that. And so let me, since we are describing different isoperimetric inequalities, there is a very well-known history of in physics of all these problems. And perhaps the oldest isoperimetric problem was solved by Sam Bernard in '56. And he asked the following question. He asked, of all the columns of a given cross-section, I mean, a given area of the cross-section, so you have a column and you cut it like that. And so of all the columns that have a fixed area of the cross-section, the one that maximizes the torsional rigidity, so you want to construct a column that sort of, it's the strongest in the sense that you try to twist it and it's going to resist the most. And he proved that the circle, of course, is going to be the one that resists the most. That was a very first problem in this area. And then there is a classical book of Lord Rayleigh, which is a beautiful book to read. It's called The Theory of Sound, and that dates back to 1877. And in that book, he proposes 3 problems. I mean, he poses 3 conjectures. I mean, maybe for him they were not conjecture. Maybe he was convinced that this was true. And the very first one says that of all membranes of a given area, the circle has the minimal principal frequency. So it has the lowest frequency is the lowest among all the possible shapes of membranes for the circle. And then he says, and the reason he quoted these things is that he managed to solve different geometries. I mean, he considers squares, rectangles, triangles, circles, sectors of circles. He had a long list of things, and then by going through this list, he realizes that probably this is true. And he didn't bother about proving this stuff, but he says, I mean, this is probably true. And then he says, of all clamp plates you hold like that with a given area, the circle has a minimum principal frequency. And of all conducting plates of fixed area, the circle has the minimum electrostatic capacity. So these are the famous 3 conjectures. I mean, we call them conjectures. He didn't call them conjectures. He was convinced that these were true. Huh? What is a clamp plate? I mean, in the membrane, the membrane is less rigid than a plate, right? So a plate is like this, right? I mean, there is a strongest interaction between nearest neighbors in the plane. So instead of having a second order operator, instead of having the Laplacian, you have Laplacian squared typically, or Laplacian to the 4th or 6th. So you can sort of like have a discretized version of this stuff, and you have more rigidity in the sense that if you discretize the problem, you have interaction between nearest points, and then in the membrane you only have nearest neighbors interaction. In the plate you have second nearest neighbors, and you can have even more interaction. And a vibrating plate, instead of having the Laplacian, has Laplacian square. And the boundary conditions, instead of being just holding the boundary like in Dirichlet, you sort of like you restrict also the bind. You don't let it bind. So I always say that you have it with your teeth like this. So it's not only like this, but it has more rigidity. Sorry, yeah, but that's a clamp plate. So I am going to describe the precise boundary conditions later. So these are the famous problems raised by Lord Rayleigh. And of all these problems, the very first one to be considered was the problem of the electrostatic capacity, and that was considered by Poincaré at the beginning of the 20th century. And then in 1918, Kahneman, I mean, whenever you treat problems in 2 dimensions, you try to solve them by using complex variables, and that's what Kahneman did. And so he introduced conformal mapping techniques to prove the analog of the Poincaré result in 2 dimensions. Considering the membrane, the very first result was proven by Courant in 1918, and he proved, and instead of proving the Faber-Cran inequality, he proved that of all membranes of fixed perimeter, not fixed area, the circuit has the minimum principal frequency, the lowest frequency. And then the conjecture, I mean, the first problem issued by Lord Rayleigh was solved independently by Faber and Cran. Faber is German, Cran was from Estonia, and they managed to prove it. And nowadays the result is called the Rayleigh-Faber-Cran inequality. And then Gabor Szego, he was the first to give a complete proof of the Poincaré theorem for capacity in 3 dimensions, and etc. I mean, there is a long list, and there is a beautiful book by Polya and Szego in 1951 from the Princeton University Press, where they have a whole list of problems arising in physics that have this flavor. I mean, but you don't have to be a mathematician. Sorry. Right? The capacity of I mean, this is in mathematics is called the Newtonian capacity. But if you do electricity and magnetism, you can define the capacity of typically of a capacitor, right? So you have 2 plates, and then you want to compute the shape of. I mean, you want to compute what is the maximum for a given voltage difference between the plates. What is the maximum charge the charge you put? I mean, in that sense, is unique. So when you have a capacitor in electricity and magnetism, like this, I mean, this is a plane capacitor, and you connect it to a voltage difference here. You can prove by linearity of the Maxwell's equation that the charge that you deposit here, this battery will take charge from here and put it here, and so if it was neutral to begin with, it's going to be neutral all the time, and the amount of charge that this battery draws here is linear in delta V, and so Q is proportional to delta V, and this is the capacity. This is in physics, right? But you can formalize that in mathematical terms. And this is for a 2 bodies problem, but also in 1 body you can also do. I mean, in one. So you have I mean, here you have 2 conductors, but you can think of one of the conductors to be at infinity and the other conductor here. So you put here a battery grounded to earth, and then the battery is going to pull charge from the earth, and then it's going to put it here, and Q is proportional to delta V. And this is the typical capacity that one considers. Huh? Yeah. And yeah. And what you can formalize this in terms of harmonic functions and all that. I mean, you can give them a very mathematical flavor, and that's called the Newton capacity. But and this is going to be a geometrical thing, and from all the bodies with the same volume, the ball has the largest capacity. The capacity of omega is always bigger, smaller or equal. No, and the other way around. The smallest capacity is going to be given by the ball. Anyway, that's a problem with the capacity. But you don't have to be a physicist or a mathematician to know about the isoperimetric inequalities. You can be this little cat here. I mean, if you in a very cold night, if you want to keep yourself warm and you want to radiate the least amount of energy out of you, you adopt this form, right? The form of a ball, and you can prove that, right? I mean, but you know it by sort of it's embedded in nature. Okay, and now I come to what I've done, what I have been working on. I haven't worked in all these problems, but I've been working on a very little thing here, which are the eigenvalues of the Laplacian, which is something that I described before. So if you have a membrane and you let it vibrate, and you consider you separate variables, and then you end up with this equation, the Helmholtz equation. And this is an eigenvalue problem. So you have the equation minus Laplacian u equal lambda u on the domain omega, and you can put different boundary conditions, but typically, for example, you can put u equals 0 in the boundary. These are called the Dirichlet boundary conditions. And you can prove, and that was proven by Friedrich Pockels in 1992, that using the compactness of the resolvent of that problem, you can prove that there is a sequence of eigenvalues. The first one is positive and not degenerate, and they are increasing lambda 1, lambda 2, lambda 3, and lambda n. And lambda n goes to infinity. So those lambdas are called the eigenvalues of the Laplacian, the Dirichlet eigenvalues of the Laplacian. Sure, yeah, precisely. And that was realized by Friedrich Pockels in 1892. And since this is general colloquium, I mean, the sister of Friedrich Pockels, who proved that, was Agnes Pockels, and she is very famous in physics for establishing the principles of thin films. And she published many different things. Agnes Pockels. So the one who proved what you stated there was Friedrich Pockels. And his sister, Agnes Pockels, she wasn't allowed to go to the university at that time, but she's even more famous than Friedrich Pockels, famous for thin films. She published several papers in Nature at that time, at the end of the 19th century. And she wasn't allowed to go to the university, but she became very much interested in that problem by washing dishes. And she decided to study all that very carefully, and she created the whole subject in physics, which is thin film. So that's a nice area. And associated to each one of these eigenvalues, Dirichlet eigenvalues, then there is an eigenfunction, which is in the proper Sobolev space, H01. And as I said before, the first conjecture of Lorraine is that among all membranes of the given area, the one that produces the lowest tone is the circle, and so this inequality lambda 1 of omega is bigger or equal than lambda 1 of omega of a ball of the same area, of a circle of the same area. And for the circle, you can solve them precisely in terms of zeros of Bessel functions. So J01 is the first zero, the first positive zero of the Bessel function for the zero. And that you can compute. I mean, those are well known, and so this quantity here is well established. And the of the circle, of the circular membrane, the precise and the result of current was it's the same thing but with L squared, not A there. And if you have the and this was proven by Faber and Kran, and if you combine the Faber and Kran result with the classical isoperimetric inequality, then you can prove current, but not the other way around. This is a weaker thing than this stuff, and that was the very first result. And Edgar Kran not only proved the same thing in 2 dimensions, but you can consider the Laplacian in higher dimensions, in D dimensions, in N dimensions, and he proved the equivalent result for N dimensions. And in all these cases, you have equality only if the domain is a ball, or a circle in 2 dimensions, a ball in higher dimensions. And one of the ways, probably the simplest proof of this result is using something called rearrangements, which are one of the tools to prove all these results in spectral geometry. So suppose that you have a domain which looks like, and you have a domain that looks like the exterior thing here, which is not rounded, and then you draw the level sets. So what I'm drawing here are the different level sets. So this is you have the ground state of the vibrating membrane, and for the ground state of the vibrating membrane, the first, you can prove that the first eigenfunction is going to be positive, and for that you can draw the level sets. So when it's sort of like vibrating, the amount of vibration here, it's going to rise and go higher and lower, and so you can say this is a level set of height 1, 2, 3, etc. And then you can define a rearrangement. This is not the precise definition that you used in math, but it gives you an idea. So if this is the level sets of the ground state of the problem for a membrane of this shape, you can now do the following thing. So consider, instead of this curve here, a circle with the same altitude, the same level here, but and the same volume, the same area, and that's what's described here. So starting from this level set 0 here, you can draw a circle with the same area than that, and then you go to the second level and you do the same, but you do a concentric circle. And so these are the level sets for the original function u, and these are going to be the level sets of what we call the rearrangement of that function there. So you have this would be sort of like a rough mountain, and this is going to be like Mount Fuji, right? Very smooth. And so, and that's a way to define the level set. And you can sort of give a precise definition in terms of measure theory, but if you remember this picture, it's clear what you mean. When you have the vibrating membrane, right? So originally what you do is the following: for the vibrating membrane, you have that thing, the wave equation, and then you separate variables. So you say u is a function of t times a function of r of the geometry. And so you do separation of variables, and then you are going to have this equation, and this is separation constant. And then you impose Dirichlet boundary conditions, so you have that, right? And then, well, I called it 5, but in that picture I call it U. So you can suppose you take the lowest eigenvalue. For the lowest eigenvalue, you can prove that that you have the maximum principle, so this guy is going to be positive definite. And then for that guy, you have a positive definite function, which is the solution of the Helmholtz equation. And then you're going to have, this is the shape of the membrane, and you can draw the level sets of phi 1. Yeah. Right? And then, if given phi 1, you can define phi 1 star, which has the same, so the level sets are obtained from those by using circles that enclose the same area. And that's well, you can, this in fact, the precise definition of that is more or less that, right? And so this is these are the level sets of phi 1, these are the level sets of phi 1 star. And this is rough, and this is smooth.
A level set that consists of two connected points. So
Here.
What do you do with that?
And the same thing, I mean, so if you see it from here, you're going to have a mountain like this, right? A rough mountain. And on the right, you're going to have a Mount Fuji. Right? Very.
So you write the lengths of the two connected.
Yes, yeah, precisely. And then you can prove, so it's easy to see, it's easy to have an intuition on that, but it's not easy to prove. You can prove the following theorem. I mean, of course, by using measure theory, the integral from the construction there, the total mass, the integral of u squared is equal to the integral of u squared dx there, by using Levesque integration, right? By the definition of Levesque integration, this is trivial, right? But so that's more or less obvious from Levesque integration, but these ones are not obvious. But more or less you can have an intuition here. So this you can consider the L2 norm of gradient u and gradient u star, right? And here, when you consider this problem, when you have a rough mountain like this is just an intuitive argument. But if you have a rough thing here, the L2 norm of the gradient is going to be larger than this nice smooth guy, right? So, I mean, the intuition is clear, but the proof is not so elementary. So the third inequality here is very intuitive, but not obvious, right? And that was proven by many people, but it's in the book of Hardy, Littlewood, and Polya, and there's a nice proof in the Talentis works and all that. And what you use, in fact, is you use Levesque integration, and you use the classical isoperimetric inequality for the level sets. So behind that proof, it's in all these cases you have the classical isoperimetric inequality. And also, if you rearrange two functions, u and b, towards the center, this is also obvious, right? So you have a function u and b's which are sort of like not rearranged towards the center. The product is going to be not such high, but if you sort of like push them towards the center in the same way, this is going to be larger than that, which is also intuitive but not easy to prove, etc. So these are the basic elements of, yeah. The what?
The inequalities. The first one goes.
So you have two functions, say in one dimension, right? So you have a function u like that, and a function b like that maybe. This is u and b, and you rearrange u as I told you before, and B as I told you before, and the inner product of these two guys is going to be larger than here, because the maximum of the functions is going to be at the center. This is not a proof. This is just intuitive. Anyway, so pay attention to that. I mean, that's obvious from Lebesgue integration. That's intuitive from what I said, the rough mountain and the smooth mountain. And so if you want to prove, and these are references, but I'm going to skip them, but if you want to prove the Rayleigh-Faber-Krahn inequality, you use the variational characterization of lambda 1. So lambda 1 is the infimum of this quotient among all the functions in the proper function space. And you can prove that the infimum is attained. That's not so difficult to prove. So if the infimum is attained, call it U1. So lambda 1 is going to be this quotient. Now you rearrange U1 in that fashion, and then the L2 norm of the gradient is going to be bigger than the L2 norm of the gradient of that, and this stays the same. So the quotient is going to be, this quotient is going to be higher than that. U1 star is not going to be the minimizer for that thing. So this one thing is going to be bigger than the quotient that you attain when you minimize this thing. So this is going to be larger than lambda 1. So lambda 1 of omega is lambda 1 of omega star. So in order to prove the Rayleigh-Faber-Krahn inequality, you have to rely on the what I told you for the gradient. So that's essentially what Faber and Krahn did, right? But right now there are very nice ways to do it, and if you remember that, you're going to remember the result. Okay, and you can also do the same thing, but with Neumann boundary conditions. So Neumann boundary condition is you have a free boundary conditions. So and you can prove by standard techniques in variational calculus that if you have a free boundary, the function u there, the normal derivative is going to be 0, right? And then the Neumann problem is the same thing here, but with this boundary condition instead of the Dirichlet boundary conditions. And you can prove, well, for the Neumann problem, you can prove also using compactness theorems that there's going to be a sequence like in the PUC stuff, and the very first eigenvalue is going to be 0, because if you have free boundary, the function u equal a constant, u equal 1 is going to be satisfying this and that. So the first eigenvalue is going to be 0, and the first non-trivial eigenvalue is going to be mu1, which is going to be strictly bigger than 0. And then you have the whole sequence. And in 1954, using conformal mappings, Gabor Szego proved that mu1 of omega is smaller than mu1 of omega star. So among all membranes of a fixed volume, the one that attains the largest, I mean in the Rayleigh-Faber-Krahn inequality was the lowest for the lambda 1, but here is the largest, and he proved that this result here. So you attain the largest for a fixed area, for a fixed volume in a higher dimension. You attain the largest one when the shape of the domain is a ball. And Szego used he was in 2 dimensions, and he used conformal mappings. And that was extended to any dimension by Weinberger in 1956. And he proved the same thing, but in higher dimensions, and among all the domains in higher dimensions, the one that attains the highest first non-trivial eigenvalue is the ball. What? P. No, P11. So this is P11 is the first positive 0 of the derivative of this guy, and the derivatives appear naturally because of the boundary condition. So that's the standard name, P11. I don't know why it's called. That's J1 is the Bessel function for the 1. But you see when you solve that problem, is, I mean, there is a whole difference with the Rayleigh-Faber-Cramp problem, because in the when you are considering the lowest eigenvalue, when you have a circular domain, the lowest eigenfunction has spherical symmetry, right? But here, since we are considering the first non-trivial eigenvalue, they have to be, the functions are going to be orthogonal to the constant, so they are not spherically symmetric anymore. So the functions are going to have, I mean, for the circles, they are going to, if you have a circular domain and you are considering the Neumann problem, when you are considering the equation, you are going to have degeneracy. It's not going to, and there are two functions that are associated to mu1. That one and that one. So these are the nodal domain, right? So you have the degeneracy of the ground state. You don't have uniqueness anymore. You don't have positivity, and it's much harder to prove than the standard stuff. So it's not comparable. I mean, Rayleigh-Faber-Cramp is not comparable to this. This is more sophisticated. And there are lots of different inequalities. I mean, the literature on these inequalities is huge. So there are many results. I mean, and in particular, Shego proved that result. I mean, you can consider mu1 and mu2. And in fact, mu1 and mu2, when you have a circle, mu1 and mu2 have the same frequency because there is a degeneracy, right? Okay. And then you can keep going on, right? And one of the simplest problems that you can think of in the case of the Dirichlet eigenvalues, instead of considering just lambda 1, you can consider, say, the quotient between lambda 1 2 and lambda 1. And the quotient doesn't have, I mean, since this scale of scales like 1 over length square, and this also like 1 over length square, this is independent of the size of the domain, right? And so in 1955, Larry Payne, George Polya, and Hans Weinberger, they computed lambda 2 over lambda 1 for a set of different figures in 2 dimensions and in high dimensions. And in particular, they managed to prove that among all the domains, I mean, here you don't have to keep the area fixed because it's independent. And they managed to prove that this is always less or equal to 3 in 2 dimensions, or 1 plus 4 over n in higher dimensions, right? And and then in that papers they say, well, we conjecture, I mean, given all the figures that we can think of, they conjecture that this was going to be maximized when the domain is a ball. And you can do that for rectangles, I mean, the way that Euclid did. So you can compute exactly lambda 2 and lambda 1 for all rectangles, and you can prove easily, because you have exact formulas for these things, that among all the rectangles of a given, you don't need to have even area, a given area, but among all the rectangles, the one that optimizes the lambda 2 over 1 lambda 1 is the square. And that's easy to prove. I mean, that you can, that's an elementary thing.
But the quotient is 3?
Huh?
The quotient is 3?
For the square,
no, it's not 3. Yeah, it's not 3. I don't remember exactly what's the value, but it's less than 3 for sure. I forgot the name. I mean, but I should have known. But it's not 3. 3 is too high for that. So for all domains, this is 3, but for the square, it's not 3. And this is not attained. 3. I mean, and then they conjecture that the maximum is for that is going to, among all the figures, is going to be obtained by the ball. And together with a classmate of mine, yeah. Huh? Yeah, this is the maximum. So they conjecture that the maximum was going to be obtained by the ball, and only by the ball. And so if the maximum is, if you have a quantity So lambda 2 over lambda 1 is less or equal than lambda 2 over lambda 1 of the ball. And you have equality only for the ball. Yeah. And we solved that with Mark Ashman was a classmate of mine in graduate school, and we solved that problem a long time ago, like 30 years ago. That's terrible. And we managed to prove that thing. But then there are, related to your question, there are stability results, right? So suppose you have a domain omega for which lambda 2 over lambda 1 is very close. So this value you can solve it in terms of series of Bessel functions. So it's J11 squared in 2 dimensions is given by that. The first and the first zero of the Bessel function for the one, the first zero of the Bessel function for the zero, because you can compute this and this precisely. But given your question, it's very important to study the stability of this result, right? So if you have a quotient, I mean, you have a domain omega for which the quotient is very close to the quotient of the ball, you can ask yourself whether your domain is close in some sense to a ball, right? And that was proven, and the stability result was proven by Melash in 1992. Of course, you have to impose convexity, because you can, I mean, if you have a domain that has spikes, you are going to have problems. But if you avoid the spikes, then you can prove that if your quotient is very close to this value, omega is going to be contained between two spheres that are closely related. And there is stability results for all these inequalities. Yeah. Yeah. I didn't want to go into all the stuff, but like in 1991 we proved this in Rn for domains in Rn. Then in 2001, together with Mark Ashford, we proved the same results in domains on the sphere on Sn. And then with a PhD student of mine, Helmut Linde, in 2007, we proved it for domains in the hyperbolic space Hn. And there are many different results in and you can prove it for Gaussian spaces. Yeah. And for the clamp plate, the equation for the clamp plate, as I said before, instead of having the Laplacian, you have the Laplacian square. And the clamp plate boundary conditions is that U is 0 in the boundary, and the norm of gradient U is 0 in the boundary. I mean, this is what I told you before. And then there is a sequence of eigenvalues for the clamp plate, gamma 1, gamma 2. In that case, gamma 1 and the gamma 1 can be degenerate, and it was conjectured by Lord Rayleigh that of all the domains of a given area in 2 dimensions or volume in higher dimension, gamma 1 is always bigger than gamma 1 of omega star. And that was proven in 1995 by Nikolai Nadirashvili. The real problem for the clamp plate, the clamp plate sort of like makes sense in 2 dimensions. So that was proven by Nadirashvili in 1995. And then we proved it independently with different methods for 2 dimensions with Mark Ashford. But we also gave a proof in 3 dimensions, which is not sort of like a physical. I mean, you are not going to have a clamp plate in 3 dimensions, but mathematically the problem makes sense. And we also proved in that case. And it's not known, and probably maybe even not true, that if you have higher dimensions, that this is true. And that's an open problem. Okay, so there is a huge literature on these things, starting from the classical results of Faber and Kran. And you can ask yourself, what is the shape of the domain that maximizes the second eigenvalue, lambda 2. And for that, it's known that for the second eigenvalue, if you want to maximize the second eigenvalue, you consider 2 disconnected balls, which is like that, etc. But not, I mean, and there are many papers on that, but there's a nice review book by Antoine and Rowe from 2017, where he describes the status of the problem like, I mean, this is contemporary more or less. And then you can consider what happens to lambda, if you want to maximize lambda 1, this is the classical Faber-Cran. If you want to maximize lambda 2, you have two balls. For lambda 3, it's not proven, but it's conjecture. It's a circle again. For lambda 4, you have the, I mean, and then up to here you have circles, circles, circles. But from lambda 5 on, you have these crazy domains like that. And they prove that there exists a domain that minimizes the thing, but the real shapes are obtained numerically. What? Sorry?
They all have smooth boundaries?
They have a smooth boundaries, yeah. Sorry. Yeah. But these are numerical stuff, right? So what they do is they prove the existence and regularity properties of this domain, and then I still have like 5 minutes, but there are many other questions that you can ask yourself, and one of the questions that people ask is the connection between the Neumann eigenvalues and the Dirichlet eigenvalues. And it's very easy to prove that mu k minus 1 is always less or equal than lambda k. That's easy to prove. But Payne in 1987, he conjectured that not only for k minus 1 here, it should be less than lambda k, but mu k should be less or equal than lambda k. And in one, so for k equal 1, that's obvious, because you can use the Szego-Weinberger result. So mu of u1 of omega is less or equal than mu 1 of omega star for the disk. And this is a number that you can compute exactly, and you can compare with lambda 1 of omega star, and this is true. And this is by the Rayleigh-Faber-Cran inequality, this is lower than that. So for the first eigenvalue mu1, the first non-trivial Neumann eigenvalue is always less or equal than the first Dirichlet eigenvalue. But what Polya what Payne conjectured in 1987 is that this is true for all k, and this was proven independently by that was proven by Friedlander, not independent, but there are different independent proofs. So Friedlander in 1991 he proved that, and there are many different proofs of different complexity, and Rafe Maceo gave a different proof of the Friedlander result in 91. And the easiest way to prove this was a theorem of Filonov in 2005, which is really elementary. So that's one of the things that was proven. And there are many other problems which are open, and some of these problems sort of like drives me crazy. But one of the things that was conjectured in the paper of Payne, Polya, Weinberger in 1955 was that not only lambda 2 over lambda 1 is maximized by the disk, but if you are in 2 dimensions, the sum of the first of lambda 2 and lambda 3 divided by lambda 1 is maximized by the disk. I mean, you can also include lambda 1. So, I mean, this would be, maybe it's more appealing to put lambda 1 plus lambda 2 plus lambda 3 divided by lambda 1 is less or equal than that. But the first term cancels if there is a 1. So that's an open problem, and there are many open problems like that. And I think I'm going to skip them because I want to go to a different, I mean, I have like 2 minutes and I wanted to go to I'm going to skip all that. But here I have one sort of like easy problem to state, which also drives me crazy in isoperimetric inequality, and this is what I call the problem of the curve. And it came from considering something called the Liptirian inequalities, which have to do with the stability of matter. But I'm not going to say the origin of that, but I'm going to quote the problem, because maybe you have you can have a solution. So these are going to be the last two transparencies. So consider a curve in the plane, say convex. I mean, it's not so terrible if you don't have convexity, but you can prove that convexity sort of like improves things. So consider a convex curve of a fixed area, of a fixed length, and S here is the length. I mean the length parameter here inside the curve. So consider curves of length less than 2 pi, and the 2 pi is just for normalization, so it's not important. And consider now this operator minus d2 ds2 plus a potential. So this is like a Schrödinger operator. So you have minus d2 ds2, s is the curve length, and you have here as the potential the curvature. Kappa is the curvature at this point, etc. That's going to be a function of s. And so you consider here like a Schrödinger problem with the kappa square as a potential. And the problem, which is still open, is to prove that, I mean, this thing is defined in a compact set, so it's going to have a sequence of eigenvalues, and we worry about the lowest eigenvalue. And so the problem the open problem is to prove that among all curves of a fixed length 2 pi, if you change the 2 pi, this thing is going to change, but very easily. So among all curves with the length of 2 pi, for all of them, lambda 1 is always bigger or equal to 1. And in this problem, the optimizers, I mean, we have done lots of numerical stuff here, but we believe that the optimizers are some sort of ovals, which are defined through this equation here. So the optimizers are curves for which the curvature in terms of S is given by one parameter family given by that. So A here is a real number. And so I mean, we know that we can prove that for all these curves, you have lambda 1 is equal to 1. And in particular, this one parameter family of curves includes the circle. I mean, for the circle, take A equal 1, so you have 1 over cosine square plus sine square, so kappa is the constant. And then try to prove that. It's very easy to prove using Fourier series that lambda 1 is bigger or equal to a half, which is not 1, right? So that's elementary. And the best bound today was obtained by my PhD student Helmut Linde in 2006, and he proved that lambda 1 is bigger than 0.608 or something like that in terms of fundamental constant pi and things like that. And that's all I want. So sorry. So I cannot go back. Sorry. Well, I don't know. I want you to solve that problem. I mean, if you solve that problem, I could die happy. So thank you very much for everything, and thank you for the invitation today. Please, one question, because otherwise I'm going to die immediately.
The Schrödinger operator.
Yeah.
So what is the physical conditions
The problem comes from something called the Liptirian inequalities. That doesn't have anything. The Liptirian. Just one word about the Liptirian. So suppose you have a Schrödinger operator in one dimension or in higher dimension, but let's say in one dimension, right? So you have a Schrödinger operator, which is minus Laplacian. Well, in one dimension would be minus the 2x2. Say in one dimension, but you can also consider this in any dimension, plus a potential negative. And suppose that V is negative, so it's something like that, right? This is V of x. And this guy is going to have a discrete spectrum, call it E1, E2, E3, that accumulates at 0. Right, and so the Liptirian inequalities are inequalities of this form. So you can consider this the sum of, I mean, this is our negative. Consider these guys as a to the power gamma. Maybe there are an infinite number of these guys, but consider that sum. And the Liptirian inequality is a relation between that sum and the integral of Vx. Vx is negative, but if we had positive part, just consider the negative part of the potential to the power gamma plus. In one dimension, it would be 1/2. And so these things, you can prove that there is such an inequality here with some constant. And the constant is going to depend, and this is we're in one dimension here, and it depends on gamma. And there is and these are called the Liptirian inequalities that are used in the proof of the stability of matter. Liptirian inequalities. And those were introduced in 1975. In the proof of the stability, Walter Tyrrell, yeah. Elliot Leib and Walter Tyrrell. And they had a proof of the stability of matter. Stability of matter means that when you consider a system with a number of particles, that the energy of the system is bounded from below. The energy per particle is bounded from below by a constant, the negative constant. And it doesn't diverge. So this is the stability of matter. And one of the ingredients in order to prove that was this thing here, but not in one dimension, in C dimension, right? So instead of having that. And these are well known. And there is one problem is to find the best values for these things. This is an interesting problem. So find best values for lambda. And no, it's not completely open. So if you have gamma equal 1/2, this is gamma. The best values for 1/2 are known. From 3/2 on, they are known. And there is an open interval here, 1/2 and 3/2, which are not. And there is a conjecture that says that if you want to obtain the best constant here, consider potentials that have only one bound state. And this is called the Liptirian conjecture. And we managed, with Michael Loss, we managed to relate this problem to the problem of the curve. So the problem of the curve arises from this sort of thing. It's a nice, sort of like a crooked, I mean not crooked, but I mean it's a nice, the formation of this problem produces the curve problem. And so if this is true, the solution for the curve problem should be what I told you. And if we solve the curve problem, this is not, I mean, so this is stronger than our problem. This is in dimension 1. And there are similar open problems in higher dimensions too.
But then you what?
No. Our problem of the curve comes from dimension 1 only. From higher dimensions, we don't have any connections. At least not that we realize.
There's a beautiful proof of the classical isoperimetric line by Hurwitz, 1901.
By Hurwitz, yeah.
So he took the curvature and expanded to the Fourier series.
Yeah.
And you get a very quick proof. I tried once to extend it to higher dimensions, but I failed.
Yeah. So this is one of the nicest proofs of the classical isoperimetric while using Fourier series, right?
Exactly.
And that's in the book of Curran. That's in the book of Curran Kilburn.
Yeah. Are there any extensions to higher dimensions?
Not that I know. Yeah. And that proof is beautiful.
Very beautiful.
Yeah. Yeah. There are proofs that are related to our problems too. They use the support function and all that stuff. There are many different proofs of the classical isoperimetric inequality right now.
I was also wondering, lambda 3 over lambda 2, any...
Yeah, we don't have we have a result from lambda 3 over lambda 2, but we haven't proved that what the maximizer is.
We don't know.
No, but I mean, with Mark and well, there are several review papers on this stuff, and I can give them all to you. But they are in the reference. I am going to give the to leave these slides here, but in the slides I have a page with reference.
So there's this Poincaré paper in 1903
Yeah,
about
the electrostatic capacity.
right. What kind of techniques?
I don't know. I don't know. But potential theory probably. But the first real proof was done by Kahneman using conformal math.
Right.
And then Poliashego, they use potential. They use rearrangements and potential theory. That book, the book of Poliashego is a really nice one. Poliashego. It's in a series of. There is a series called. I don't remember the exact name of this. So it's not an Annals of Math, but it's sort of like Annals of something. There's a collection of. Some analysts. But anyway, I have the exact reference there, and that's 1951, and that's a beautiful book with lots of open problems. What happened? What?
When you have like, for example, you show that if you have lambda 2 of lambda 1 is close to the when you consider the like other function, like the I don't know how to say that, like this mixation and all. Like you prove the inequality.
Yeah.
And like you show that it's stable, like if the ball is closed, then it must be like close to the circle.
Yeah.
Like this must be like somehow true, like if you consider like lambda 2 over lambda 2,
Yeah.
or like lambda 4 over lambda 3.
Yeah.
It's expected to be true. Like this.
Yeah, I don't know.
Polygons.
Huh?
You said for rectangles, you always have this inequality.
And yeah, for regular polygons,
Is always the problem is always for the regular polygon is minimized.
yeah, but it's for the capacity there is a result for all the regular polygons. For the eigenvalues, there is no proof of that. And in fact, there is a recent paper by some undergraduate students of Princeton that proved the Payne-Polya-Weinberger result, our result, among all rectangles, among all triangles, and they consider the quotient of these two things among all triangles, and they prove that the highest value is obtained for the equilateral triangle. But that's not easy, and that's not true. Sorry, that's not known for a regular polygon. So sometimes the problems with the polygons are much harder. For capacities, this is known, right? If you want to have capacities are obtained among all the polygons by the regular polygon.
About that inequality, choosing the first eigenvalue for the ball and a region. If it's not equal but slightly smaller, can it happen that two regions have the same first eigenvalue or they are isospectral?
If you have two different regions of different. Right.
Is uniquely determined.
You can, since you know how they scale with the size, you can determine. If you have for a given size the eigenvalue lambda 1. So you want to have a domain like this, right? And then you can compute lambda 1 of this omega, and you know what happens when you dilate this domain, right? No, but you can. That's easy to determine. If you dilate, by monotonicity, this is going to diminish. If you dilate, lambda 1 is going to be monotonically decreasing with the dilation. And so there is one value of the dilation for which you can fix this stuff to be equal to something else. I mean, these are monotones under dilation. If you rotate, nothing happens, right? Yeah, yeah, but under dilations, they are monotonically decreasing, right? Yeah, 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 sure, yeah.
Is there a sort of like a stability result of the following type? Suppose you know that you have two regions and they have, one of them is maybe this, okay? And the other one has eigenvalues which are very close to the ones for this.
Yeah, I don't
Can
know.
you show that this region is, say, convex?
Yeah, I don't know. That I don't know. The only thing about stability that I know are the results of Melash. Yeah.
And I have another question.
Yeah.
What is the connection with this famous paper by Mark Katz? You know, can you hear the shape of the drum?
Yeah.
What is there a relationship here?
There is a the only connection. I mean, yeah, sure, there is a connection. Yeah. So in the problem of Mark Katz, the problem is to given the eigenvalues is to determine the shape of the domain, right? And the question, the answer to that problem was no. I mean, that is the theorem of Caroline Gordon and Wolpert and Webb, right? So the problem Mark Katz is, can you determine the shape of omega given the sequence of these guys? Yeah, and the answer is no, and that was proven by Caroline Gordon, David Webb, and Scott Wolpert already in 1992. So Caroline Gordon, yeah, and David Webb and Scott Wolpert. They proved that it's not possible, right? They proved that there are two domains in two dimensions that are not isometric, and they have the same spectrum. Yeah, this is well known, right? But in terms of rearrangements, there are. I mean, so one of the things that they consider that you can, in order to prove that, you can consider what is called the trace, that quantity there, the zeta function, right, which is related to the Riemann theta function. So you can consider that, and this C is, of course, I mean, depends on the geometry through the lambdas, right? And you can ask yourself what happens when you rearrange. So this C of omega T depends on the geometry. And you can ask yourself what happens when you rearrange the domain and consider this ball, and can you compare with the ball? And that's known. I mean, there's a paper by Lattinger and Friedberg. I forgot the year. Lattinger and Friedberg. Well, they proved that C of T of omega is, I think it's bigger than C of omega star T. So there is a connection between the two. Thank you very much.